Find all zeros of p of x equals x cubed minus 7x squared plus 17x minus 15. In this case, we won't be able to factor this polynomial by grouping the first two or the last two, or even any combination of these. Observe that this polynomial has three variations in sign: positive to negative, negative to positive, and then positive to negative. What that means is that this polynomial has either three positive real zeros or one positive real zeros using the Descartes rule of sign. Using the rational zero theorems, we see that the possible rational real zeros are of the form p over q, where p's are factor of the constant coefficient negative 15. The factor of negative 15s are plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 15. And the factors of the leading coefficient 1 is plus or minus 1. The possible real rational zeros are therefore only plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 15 over plus or minus 1, or themselves. Checking if x equals 1 is a real zero, we perform synthetic division. We write k equals 1, draw the vertical line, and write the coefficient of the polynomial starting with the leading coefficient. The leading coefficient of x cubed is 1, the coefficient of x squared is negative 7, the coefficient of x is 17, and the constant coefficient is negative 15. We bring down 1 and multiply k. 1 times 1 is 1. Write it in the next column. Negative 7 plus 1 is negative 6. Negative 6 times 1 is negative 6. 17 plus negative 6 is 11. 11 times 1 is 11. Negative 15 plus 11 is negative 4. The remainder is not 0, and so x equals 1 is not a real zeros of this polynomial. The synthetic division also reveals something to us. The last entry alternate in signs: positive to negative, negative to positive, positive to negative. This is significant because the lower and the upper bound theorem states that x equals 1 is the lower bound of all of the real zeros. This is useful because we don't need to check if x equals negative 1 is the solution. We don't have to check x equals negative 3 is the real solution, or negative 5 or negative 15, because x equals 1 is the lower bound of any real solutions. This means we just simply check the positive possible candidates only. The next one is x equals 3. K is 3. And we write the coefficient of the polynomials: 1, negative 7, 17, negative 15. And we bring down 1. 1 times 3 is 3. Negative 7 plus 3 is negative 4. Negative 4 times 3 is negative 12. 17 plus negative 12 is 5. 5 times 3 is 15. Negative 15 plus 15 is 0. This means x equals 3 is a real zeros of p of x. This allows us to write the polynomial in factor form, with x minus 3 being the linear factor. The remainder is 0, and so the coefficient on the left-hand side is the constant coefficient of the quotient. The number on the left-hand side of it is the coefficient of x, and the number on the left-hand side of it is the coefficient of x squared for the quotient. And so p of x is x minus 3 times x squared minus 4x plus 5. To find the remainder zeros, we can either try to factor it, in this case we won't be able to, or use the quadratic formula to solve for the complex solutions. This quadratic expression has a equals 1, b equals negative 4, and c equals 5. The discriminant d is b squared minus 4ac. b is negative 4, a is 1, c is 5, and so it is 16 minus 20, which is negative 4. So we know that it doesn't have any real solution. The solution will be complex. X equals negative b plus or minus the square root of b squared minus 4ac over 2a equals b is negative 4 plus or minus the discriminant is negative 4 over 2 times 1, which is 2. This is 4 plus or minus the square root of negative 1 times 4 over 2. And so it is 4 plus or minus the square root of 4 is 2, and the square root of negative 1 is I over 2. Factor out 2 in the numerator. We have 2 times 2 plus or minus I over 2, and the 2 canceled out. And so the three zeros are x equals 3, x equals 2 minus I, and x equals 2 plus I. If we want to write the polynomial p of x in factor form using complex number, then we can factor this as x minus 3 times x minus 2 minus I times x minus 2 plus I. Don't forget that we would have each linear factors at x minus the 0, x minus the 0, x minus the 0.